You have probably experienced this sudden shock. You accidentally brush your hand against a glowing element, and your body reacts before you can even process the event. That searing pain is your nervous system registering a massive, instantaneous invasion of energy. For centuries, scientists believed heat was an invisible fluid that flowed into objects like water into a sponge. But heat is not a physical substance. It is strictly kinetic energy, the microscopic, chaotic motion of atoms and molecules within a material. This kinetic energy follows one relentless rule. It always flows spontaneously from a region of higher temperature to a region of lower temperature. Energy drains out of the hot object and into the cold one, never the other way around. This transfer continues until the temperatures match exactly and the flow stops. This state is called thermal equilibrium, a condition where two systems reach the same temperature and the net exchange of energy ceases. Heat transfer is the universe's inherent mechanism for eliminating temperature imbalances and restoring stability to an environment. To see this mechanism in the physical world, imagine a metal spoon resting in hot soup. Within minutes, the handle becomes too hot to touch. This happens through conduction. At the atomic level, the particles in the spoon absorb energy and begin to vibrate violently. These particles collide with their neighbors, passing the kinetic energy up the handle step by step, even though the metal atoms themselves never leave their fixed positions. We measure this efficiency using thermal conductivity, a physical property describing how easily a substance transfers heat. Metals are highly conductive because their tightly packed atoms spread vibrations instantly. But loosely structured wood molecules trap energy, acting as insulators. This causes an illusion. Room temperature metal feels colder because it drains your body heat faster. Conduction requires direct physical contact. The energy travels efficiently through the material, but the matter itself remains completely stationary. In liquids and gases, heat behaves differently. Look at a pot of water actively boiling on a stove. Heated water molecules at the bottom spread apart and expand. This less dense layer floats upward, while cooler water sinks to replace it. These continuous loops are convection currents, which require the physical movement of matter to transport heat. When we scale this mechanism up to the size of a coastal beach, it explains the very origin of the wind. During the day, solid land heats up faster than the ocean. The air above the hot sand warms, expands, and rises high into the sky. This creates a low-pressure void at the surface, pulling the cooler, denser air from the sea toward the land. We experience this atmospheric shift as a sea breeze. This physical transport of thermal energy through convection acts as the global atmospheric engine driving the weather patterns of our entire planet. High above that beach sits the sun, the source of nearly all life. But its heat must cross 150 million kilometers of empty space to reach us. In the vacuum of space, there are no particles to collide for conduction, and no fluids to circulate for convection. For energy to cross the void, it needs a third mode of transfer. That mode is radiation. The sun transfers its heat using electromagnetic waves, pure energy that oscillates through space in synchronized electric and magnetic fields. Every object in the universe above absolute zero constantly emits this thermal radiation. Indeed, your chair, your phone, and your own body are all radiating energy into the room right now. Surface properties dictate how this energy is received. Materials that are dark and rough absorb electromagnetic waves and heat up quickly. Conversely, light, smooth surfaces reflect the energy, letting it bounce away without raising the material's temperature. Radiation is the independent distributor of energy, bridging the vacuum to sustain life on Earth. Humans have spent thousands of years learning to manipulate these three rules to survive and thrive. Look at this traditional Bukhari heater used in the Himalayas. Its metal body is designed to radiate warmth across a room, while simultaneously conducting extreme heat directly into the kettle resting on its surface. This solar cooker uses a highly reflective parabolic surface to catch incoming solar radiation. By bouncing those electromagnetic waves onto a central black pot, it concentrates the energy into usable, high-temperature heat. In Ladakh, engineers build cone-shaped structures called ice stupas to store water. The steep, narrow geometry minimizes the surface area exposed to the sun, reducing the absorption of radiation and slowing the melting process, so the water lasts through the dry spring. Energy travels through the direct contact of conduction, the moving currents of convection, and the independent waves of radiation. Understanding these laws allows us to manipulate the natural world. So, applying what you have learned, tell us in the comments, exactly how does a winter blanket keep you warm through a freezing night, when the blanket itself generates zero heat?